OK, we've talked about block ciphers and the fact that the block cipher being a permutation makes it correct. Each of these arrows points to exactly one output for all possible inputs and for all possible keys. Now let's talk about how you make these things secure. So remember, the idea behind security is Eve doesn't know K. And if she doesn't know K, she shouldn't be able to reverse and decrypt any messages that she receives. She shouldn't be able to learn anything about the original input. So the way that we are going to call or check whether or not a block cipher is secure is we're going to play another little game. In security, there's all these little games that people use to check whether or not something is secure. So formally, the mathematical definition reads like this. The block cipher is secure if it behaves like a permutation, a random permutation, sorry. So block ciphers are secure if they behave like a random permutation. But that's kind of hard to understand. It's weird and it sounds mathy. So I think a distinguishing game will make things more clear. So here's the distinguishing game. So you are Eve. All of you can play Eve. That's you with little horns. And I am going to give you two boxes corresponding to two different universes. So this box is one of the boxes. This is the other box. And I'm going to tell you, in one of these two boxes, I have placed the mapping that was generated from E using the secret key. Remember, the scheme is that Alice and Bob are talking with a key that Eve doesn't know. So in one of these two boxes, the way that I drew the arrow is I picked the key that narrowed it down to one of the mappings, and I produced that mapping in the box. So if it was this one, that means that if I use the secret key that Alice and I are using that you don't know, then when I use that key to encrypt 0, 0, I get 0, 1. When I use that key to encrypt 1, 0, I get 1, 1, and so forth. So one of these two boxes, and I'm not telling you which one, was generated by using the secret key and drawing the arrows according to that secret key. In the other box, I dropped in all the arrows at random, and you don't know how I dropped them in. So for example, if this was the random box, then it means that for 01, I just picked one of these 4 inputs at random, and for 00, I picked one of these 4 outputs at random, so I drew the arrow here at random. And for 11, I picked this one at random. So I dropped these arrows basically in any random order that I could think of. Now the challenge for you, Eve, is you need to tell me which one is which. Which of these two was generated by using the block cipher algorithm, the code in this box, with the key that Alice and I chose to use? And which of these was generated by randomly dropping in arrows? What do you think? Which one is which? Hopefully you can't tell, because I can't tell either. And that's what makes the block cipher scheme secure. When we say it behaves like a random permutation, we're saying that if you present Eve with something that was actually generated from the block cipher and something where I drew all the arrows at random, Eve cannot tell which one is which. One of these was generated with actual code. One of these was generated by dropping arrows at random. And Eve is unable to guess which one is which. The best she can do is a coin toss. So what that means, to make a long story short, is that once you narrow down one of these tables, remember there's all these different ones in a family, you pick a key, it narrows down to one of these tables, Eve has no idea how to build the table because it looks totally random. From Eve's perspective, the table might as well just be random arrows dropped in, so Eve is totally clueless as to what inputs map to what outputs. So because the block cipher behaves like random, that means Eve has no idea which table is being used because she doesn't know K. And if she doesn't know what the table is, she has no idea how to generate it because it basically looks random. That's the proof. It's kind of a cute little proof that you have to stare at a little bit, but that's how you do it. OK. Now that we know how block ciphers are secure, let's start thinking about various attacks on it. So one possible attack that you can do on a block cipher is the brute force attack. This is kind of the attacks that we saw last time when we saw the Caesar cipher and so forth. And what you want to do is just try every key. Take the message, decrypt it with every possible key. And remember, for each key that you choose, you get a unique mapping of n-bit inputs to n-bit outputs. So try each one and see which one you like. You can try that. But if we have a key that's 128 bits, that's going to take you a long time. And I mean really, 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 really long. So for example, if we have a 128-bit key, that means that we need 2 to the 128 different possibilities, that's a really, 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 really big number. And so using a bit of back of the envelope calculations, this number is so big that even under some very, very fast assumptions, you would need something like 30 trillion years to solve this problem and guess the correct key. So you can try it. You can try to take my encrypted message and guess it, but you're going to be sitting there for 30 trillion years before you can tell me what the message is. So you can try it, but you're not going to finish. The universe will swallow us all up before you are ever done. And it turns out, if you try 256-bit keys, well, now you need 2 to the 256 different possibilities, and now you'd have to have like you'd have to stack all these computers, and they'd all have to work in parallel, and even then it would still take trillions of years, and the number of computers you stack in parallel would like not even fit in the sun. So what I'm saying here is that this is just too big to brute force. So yes, it is technically possible for attackers to try and brute force block ciphers, but as long as you use a key that's long enough, 128 bits or 256 bits, the time it takes to brute force these keys is way too long. No one is ever going to succeed, so it's as good as secure, assuming that no one knows your key.